and welcome to this forum. This forum is a very nice subject of space medicine because life science is one of the key areas of activity of the International Academy of Astronautics. And as the Secretary General, I'm very pleased to co-host the symposium. I would like to say that in the creation of the Academy, the very famous astronauts like Gagarin or Valentina Tereshkova were members of the Academy. Valentina is honorary member of the Academy. And after 55 years, we had several events in life science. We had the life science, the Human in Space Symposium in China, hosted by Professor Liu, Professor Xuan, 4 or 5 years ago. And this year, a few months ago, there was the symposium in Cologne. The Academy is 1,200 members, and one of the sections is life science. And life science includes all the scientists of this planet, and we continue to elect every year the best to the Academy. I think that the forum today is a very interesting subject, and the speaker of this morning are a very nice audience as well as the rest of the day. So I wish a very fruitful event, and I think that inside this big congress, life science is very strong. Thank you very much.
In this forum. As you have heard already, the title of the GNF forum today is Space Medicine and Human Health, not Space Medicine and Astronaut Health. And that's because what we are doing is wishing to show you a few stories about how the development of space medicine is leading to the development of new ways to approach human health. After a long gestation period, in fact, we are witnessing the birth of a new set of guidelines and facts that will influence the way that medical science treats different conditions in the human body, not in space, but on Earth. Here in China, too, space medicine is evolving. More than 25 years ago, I was part of a NASA delegation who visited Beijing and visited what was called the ISME. And medicine is different today than what it was 25 years ago. Today, in the medical world, there are really two different directions that medicine is using to look at the body. One is the whole organism level. It's where you hear about things like the conditions of space flight that are negative, things like bone loss, things like cardiovascular problems. Then, at the same time, a whole world has opened up at the molecular and cellular level. And this is the most active world today in medical sciences. We're beginning to connect the dots between the two and draw a picture. And the picture that is emerging is able to show how the unique laboratory of space, with the unique ability to remove weight from the different parts of the body, is able to contribute to our understanding of the body. And that understanding of the body will ultimately, I think, prove profound in a number of ways. You're going to hear the stories today about that evolution, and I hope you enjoy them. Thank you very much.
I'm honored to attend and give a speech at this opening ceremony of the 64th IAC Space Medicine and Human Health Forum. From the theme of this forum, I can feel the three combinations. The first is the first combination of space research and ground application. With the rapid development of manned space flight program, the relevant study in space medicine are moving quickly. Applying the experiences and knowledge obtained in space to the human health on the ground will be a benefit to human health, and it is of far-reaching significance. The second is a combination of Western medicine and the traditional Chinese medicine. The objective of Western medicine is to find the pathogen and the target, and then suit the remedy to treat the disease. Well, the traditional Chinese medicine regards the human body as a complete system, just like a universe. And paying attention to the recuperation of a whole body by qi and xue. I don't know how to translate qi exactly in English and xue, what's the exact meaning in English. Qi in Chinese means such as gas and breeze, and means qi. And xue means blood, but it's not the same concept. It's very complicated to explain this, so you can just mention qi and xue. It's a concept in traditional Chinese medicine. And I think the former focus on treatment, I mean the Western medicine focus on treatment, while the later focus on maintenance. Chinese medicine and Western medicine have a significant emphasis, and each one has its great points for the human health from different aspects. The combination of them will promote human health and prevention greatly. The third is a combination of physiological health and psychological health. The damage of physiological health is obvious, while the problem of mental or psychological health are not easy to find. Under risk and isolated space environment, the psychological health of people arose comprehensive attention around the world. So this forum will explore the problems of psychological health beyond that physiological health. It is a demand and trends of modern times, and will also contribute to the establishment of high quality life. We are happy to see the three combinations united in this forum. I believe that the gather of experts home and abroad in space medicine and human health field today, with the full exchange, will be of great benefit to human beings and create a new and healthy future. Finally, I wish the forum have a complete success.
Congratulations to the opening ceremony. Ladies and gentlemen, traditional Chinese medicine has developed and refined over the course of thousands of years by the Chinese people for use in the prevention and treatment of disease, leading to the accumulation of the rich experience, techniques, and methods for maintenance of human health and well-being. To my knowledge, the Chinese Astronaut Center has made some interesting exploration and obtained excellent results. These earlier studies are greatly helpful to understand the role of traditional Chinese medicine in preventing and treating bone loss, muscle atrophy, cardiovascular disease, and memory impairment induced by spaceflight. And these studies are also beneficial to promote the application of traditional Chinese medicine in prevention and treatment of osteoporosis, cardiovascular and cerebrovascular disease, Alzheimer's disease, and intractable disease. So it's our common goal to strengthen cooperation between traditional Chinese medicine scientists and those scientists around the world, including those in the area of aerospace medicine, and to make contribution for maintaining the health of the astronauts. At the meantime, we hope to utilize the cutting-edge technology in the aerospace field to enhance the quality safety and efficacy of traditional Chinese medicine, and to improve the quality and efficacy and the capacity of traditional Chinese medicine to serve human being and well-being, including the astronauts. We also hope that the scientists from various areas, including aerospace and traditional Chinese medicine, can take this conference as an opportunity to increase mutual understanding and to promote collaboration with the same view to developing aerospace medicine and traditional Chinese medicine. In this aspect, the state administration of traditional Chinese medicine will provide our best support. And finally, I wish this conference a complete success. Thank you very much.
向我的同行们，还有各位专家致敬。
First, and then, please allow me to pay tribute to my peers and seniors, everyone.
3个月前呢，我和我的同事执行了这个神识任务，那是我第2次遨游太空，但是我兴奋和激动的心情和05年第1次进入太空是一样的。
3 months ago, my colleagues and I were performing the mission of the Shenzhou 10. At that time, the feeling of the appearance, the weightlessness, is really excitement.
太空是如此的美妙，能够有这种独特的体验，确实是我们航天员的幸运。
It was so lucky to experience the flight. It's one kind of unique experience.
太空既是航天员，更是全人类共同的梦想。2次太空经历让我更深刻地认识到，尽管从事的工作有很大的风险和挑战性。 但是航天员也终归是职业的一种。
With experience the risks and the challenges in the outer space, but I still think that the astronaut is one kind of career. It's like the normal workers in other industry.
无论是在太空还是在地面，长久健康的生活对我们航天员或 所有职业的从业者都是同等的重要，同样值得关注。
We should pay attention on the medicine and the medicine and the development of the medical. We need the great effort to work on the medicine career.
今天，航天医学与大众健康论坛开幕。太空这一共同梦想和健康这一永恒主题将得到完美结合。
At this moment, the forum of the opening ceremony of the medicine of the Aristotic medicine and the public health. The common dream of and the health will be combined perfectly.
借此机会，我真诚地感谢所有为了航天员健康而付出辛勤努力的人，相信这些努力也一定能够为航天医学的发展、为大众的健康和我们未来的美好生活提供更多的帮助。
Now, I sincerely thanks to the people who have paid a great effort on this on the development development of the people's health and astronomical health.
最后，预祝论坛取得圆满成功。Thank you.
Finally, I wish the forum will get a great success. Thank you, everyone.
Thank you.
Medicine and human health. Space medicine talks to our desire to prevent, to diagnose, to treat illnesses in current astronauts and astronauts who will travel in the future. But as Mr. Ron White said, equally important is human health. Look at this globe of Earth here. I'm proud that Canada is prominently depicted. In southern Canada, there are many millions of Canadians that live in large cities and have access to the best doctors, the best hospitals in the world. In northern Canada, including the Arctic islands, there's hundreds of thousands of Canadians that live there. They have equal right to health care as the Canadians that live in the southern part of the country. How do we do that? We use space medicine techniques. We provide healthcare workers with training and consultations that they need to be able to have the confidence to take care of those northern Canadians. We make use of mobile, portable space technologies to be able to diagnose and treat some of our northern Canadians. And we provide them with abundant communication and transportation resources. I had the opportunity to fly on a short duration space flight and also on a long duration space flight. The issues, the medical issues that I faced in the long duration space flight were different than those on the short duration space flight. In the future, we're going to leave low Earth orbit and we're going to venture interplanetary. We know that those medical problems will be different than the ones that we face today, and that's why space medicine research is so important. We need to keep predicting what's going to happen in the future. Ionizing radiation, psychosocial isolation will obviously be a problem with interplanetary spaceflight, but the majority of the medical issues we face in the future, we don't know what they are. So that's why space medicine, together with human health, is important. If we don't maintain the focus on human health, we'll lose relevance with our politicians and our public. Thank you.
Okay? Yeah, great. So thank you very much to the organizers, Drs. Chen, Professor Chen, Professor Lee, for the opportunity to address this distinguished audience of colleagues and friends. And I'd particularly like to thank Dr. Chen personally for his gracious hospitality during the stay here in Beijing, where we're experiencing just terrific weather and some really great discussions at this meeting. The organizers asked me to talk about this topic, a long prospect of space life sciences and medical sciences. And by that, the organizers wanted to have some perspective on what to expect in the time frame of 2020 to 2050. Of course, none of us know the future, and so some of this is speculation, but there are some assumptions that I'd like to put forward and then to talk around this. In the year 2020, there will be 20 years experience of continuous crew participation aboard the International Space Station involving 16 partner nations. China will have a space station that's operational. There will be a significant expansion of commercial human space activity. And while much of this may be suborbital, I think what we're going to see is that a lot more individuals are going to have an opportunity to experience microgravity. The duration may be shorter, 5 minutes or so, but those individuals may have some pre-existing conditions, and so therefore will experience the provocation of microgravity with concurrent medical conditions. And this will be an incredible opportunity to learn about the health and the adaptation of a very large number of people. As mentioned previously, there is the potential for missions beyond low Earth orbit, and the risks and the priorities do change somewhat. And inevitably, there are going to be extraordinary advances in scientific knowledge, discovery, technical capabilities, and advances in medicine that we can't even conceive of what they're going to be. Of course, we build on a legacy of incredible achievement in space medicine and human health. And to even begin to discuss those achievements would be the topic of the entire day. But what I'd like to focus on is that looking towards 2020, the 2050 range, there are going to be great opportunities. And these involve scientific discovery, technical innovation, and new approaches to risk, new countermeasures, new treatments, and collaborations and integration in ways, again, that are difficult to know. We do know about challenges, the harsh remote environment of space, of course radiation and microgravity, but there are other challenges as well. Need for sustainable life support, need for autonomous care, and we're aware of challenges that we face within our own countries, between countries, of national priorities, of funding, of how to coordinate collaborative activities. And what I'm going to put forward, given the challenge that the organizers put forth in this presentation, is to propose that we're really moving toward a large-scale scientific enterprise in the area of space medicine and space life sciences. And I'm going to make a case for that. First of all, there's a grand noble cause. When one looks at large-scale scientific enterprises and how they begin to form, whether it be in high-energy physics, whether it's in astronomy, or genomics, or neuroscience, you see, first of all, that there's a great cause that brings people together, often to advance humanity in some way, to gain knowledge that has both tangible and intangible consequences and results. Space biomedical research is complicated, it's difficult, and it's expensive. And so it's inherently interdisciplinary. It's technically challenging, not only from the standpoint of carrying out the science, but also looking at operational need and operational feasibility issues, constraints. And there are multiple influences that are present in the space environment. If one sees an effect, is it due to microgravity? Is it due to radiation? Is it due to both? Is it due to other causes? To what extent do these factors play a role? And hence the need to develop appropriate control experiments, and often there are situations where that becomes very difficult. And there is the utilization of limited or unique core assets. So if you look at the International Space Station, or you look at unique analog environments or simulation setups, this brings people together. Flight experiments typically involve multiple nations at the present time, whether it be international crew time or hardware sharing or infrastructure. But what we're seeing, it's apparent at this conference and at other conferences, is a growing international cooperation. There are bilateral working groups, there are multilateral working groups, people working in teams in space life sciences, and there's already a very good model in the space medicine side where the nations come together and establish standards and requirements, for example, in taking care of individuals aboard the International Space Station. We're seeing growing success in the partnerships that involve government, academia, and industry within nations. And we're beginning to see, as a community, also this triad of collaborations that takes place across countries. And we're seeing growing academic consortiums. For example, in the United States, NASA in 1997 established a National Space Biomedical Research Institute, the NSBRI, which now consists of about 60 universities and institutions that work collaboratively together to help NASA address important problems and find solutions. And that model is now being extended to look at networks that go across international boundaries. And there's an expansion in university departments in space life sciences. So there are traditional, well-established departments such as the Massachusetts Institute of Technology in aeronautics and astronautics. But we had the good fortune, Leroy Chow and myself, to visit Northwestern Polytechnical University in Xi'an prior to coming to this meeting, where there's a new department, a new and exciting activity that's taking place in space life sciences. At Baylor College of Medicine in the United States, a major top-tier medical school has established what is in effect its own department in space medicine, so that the chair of space medicine sits with the chair of surgery and with pediatrics, and that there are now academic appointments that are being made in space medicine. We're seeing new facilities with international projects and exchanges. So Dr. Rupert Gertzer talked a little bit yesterday about his wonderful facility that a number of us had the good fortune of attending the opening of in July, NVHAB in Cologne. And NSBRI and the Center for Space Medicine, in partnership with NASA, occupies now the 9th floor of this beautiful bioscience research collaborative that you see in the lower left-hand side. And there seems to be a growing consensus as to what the major problems are that people should address in space life sciences. High priority risks and problems. Not all of these problems are the same across the nations, but again, I think that people are having a serious look at the visual impairment and intracranial pressure problem, of course at radiation, life support, nutrition, autonomous medical care, behavioral health, musculoskeletal alterations. These are just a number of the risks that there is consensus upon. It's not a complete list by any means, but it's not just the risks. It's other problems as well, such as how do we deal with data sharing. And there is a projected increase in the human presence in space. And very importantly, as what was mentioned in the opening remarks, tangible applications to enhance life on Earth. So all of this is by way of saying that we are, in some sense, on a cusp of an evolution towards what I believe is a large-scale scientific enterprise. And we see examples of this. We see examples of this, of course, in the International Space Station, but I would like to give an example and compliment those individuals and a wonderful team that were involved in the successful running of Mars 500, because this is a great exemplar of what is happening today. Multinational collaboration of this first high-fidelity simulation of a crewed mission to Mars. We're very honored, actually, that the crew members are sitting in the 4th row here, and it was a unique scientific opportunity that was opened up to the world. And there were barriers for some nations to participate, for example, for the United States. And while NASA was restricted in its participation, NSBRI, which is an academic consortium that partners with NASA, was allowed to participate. And so, effectively, we had US and Russia and European nations and other nations from Asia and a crew member from China, all involved in a study. And one of the important things that came out of this was not only the opportunity to collaborate, but really to raise the bar on the caliber of the science that comes out of these international activities. And I'm very pleased that among the publications that have come out earlier this year, I had the good fortune of being the senior author on a paper in the Proceedings of the National Academy of Sciences. And without going into details of this paper, one of the things that surprised us, and I think surprised a number of people, was the enormous individual differences that existed among the crew members. And here's the wonderful crew. So looking at these happy, smiley faces, who would know what the responses were going to be when subjected to this high-fidelity simulation? And I think what it's testament to is that we're on the verge of a transformation that's taking place in how we approach space life sciences and space medicine by looking at individual susceptibilities and the development of individualized countermeasures, by looking at revolutions that have taken place in Earth-based life science and Earth-based medicine, in omics, in genomics, in proteomics, in metabolomics, and so forth. And there are now data in a number of areas that are pertinent to space life science and space radiation. For example, looking at the different vulnerabilities that individuals have to the effects of radiation and of particular types of radiation that we would experience beyond the magnetosphere of Earth. Radiation, without a doubt, as we look to the 2020-2050 timeframe, is a major, major issue. Not only the development of dosimetry, but also looking at models of the enormous heterogeneity on different organ structures that not only vary based on anatomy and physiology, but vary across individuals. And so what we're seeing is collaboration not only among the space life sciences, but bringing in others who are new to the field, radiation oncologists and those that deal with treatments and new advances and approaches to these very difficult problems. We've heard at previous workshops and parts of this conference, and we'll hear more about the incredible science that is done in space and the applications to Earth. But what I wanted to do was also to make you aware that, as you all know, of the reverse flow, and that is great discoveries that are made from funding of investigators in life science. For example, investigators who are involved in the rediscovery, really, of certain cells within the retina that are extremely sensitive to blue light in the 420 to 460 nanometer range. And the applications to space of these small cells, which probably allow animals to distinguish dawn from dusk, have resulted in blue lights that are making their way to the station, because it's known that for circadian entrainment, light intensity, timing, and duration is important, but also the color of the light is important. And so by changing the lighting, it is possible to help astronauts in the space environment. And while scientific advances from space can change medicine, and we heard a little bit about this yesterday, some incredible results looking for where salt resides within the body and under certain conditions of stress, that really changes the textbooks and the concept of how physiology works, also in the area of technology. And while ultrasound technology is not something that was developed specifically for space, by having ultrasound aboard the ISS really changed the way in which ultrasound is being used on Earth, because it demonstrated that in non-conventional imaging applications, that ultrasound was actually much better than what individuals thought. And experiments that were done aboard the ISS really brought to light, and the results were able to be consolidated into textbooks that now hospitalists and surgeons and anesthesiologists and other individuals have in their pockets when you go around the hospitals, in the clinics, based on work that was done in space. This picture, of course, is of Leroy Chow and Selezan Sharipov aboard Expedition 10 at the International Space Station. But as I mentioned earlier, we can't even begin to imagine the nature of the medical technologies and support that are going to be available in the future. But what we do see is that very smart physician scientists, engineers, and other folks from across different countries become interested in moving medicine forward. For example, in the surgical area, from open surgery to minimally invasive to completely non-invasive surgery, to completely non-invasive real-time diagnostic imaging, whether it be using near-infrared spectroscopy with multiple wavelengths, or using NIRS technology in ways that can look at functional brain imaging. Because, of course, one of the things that we're very concerned about is the potential harmful effects of radiation on the brain during a long-duration mission. And finally, I think it's important in this very brief talk to not overlook the fact that we have a new generation of individuals and bright students who are growing up in a different world with different cultures, who are keen to become involved in space life sciences and in space medicine. And these individuals are really the hope for the future. And when you look at different countries, there are different programs. This is just a summary slide from some of the programs that are offered by the NSBRI in the United States, but by no means is it complete. And it's really inspiring also to look out in this audience and see a mix of generations. And I think that as we look towards this transformation that we're now part of and heading towards 2020 to the 2050 timeframe, there are young scientists who are growing up in a world that has far fewer national boundaries that they see. And it's wonderful to watch students move from postdoctoral stage. For example, this young fellow on the left-hand side is Professor Bailey. He started as a postdoc, actually interested in space life sciences, working in ultrasound. And he and his colleagues have actually developed a technology based on space applications, but that is non-invasively able to move kidney stones that are embedded, which would normally have to be subjected to either lithotripsy or invasive procedures. It's really an amazing technology, and it's now undergoing clinical trials, and it's led to a spin-off company, and there's a lot of interest. And we're also very pleased that we see collaborations among the space biomedical research institutes in different countries. For example, United States and Russia. Here is a postdoc from IBMP, Julia Gershowitz, from Ludmila Barankova's lab, who did a postdoc with Tony Mikos, who's a member of the National Academy of Engineering and of the Institute of Medicine in the US, on a flight experiment in tissue engineering that will make its way to the station. So hopefully one day. So I think, in conclusion, that really we're on the verge of something very exciting, in my opinion, and I think in the opinion of others, and that the implementation of large-scale research program, it's achievable, and it's of great value. And at the heart and soul of this, of course, are the people and the desire to do this from many nations, and hence the importance of international cooperation as a key component. So thank you very much.
Any questions or comments? Yeah, of course, maybe for me, many questions, but maybe it's hard to give the explanation. For example, you just said related with kidney stone. We can remove the kidney stone. What kind of innovation? Or if it is simple, you just then if for too long, then we discuss it later. If you can some simple words can give some little explanation how to relate it with space medicine.
Right. Well, I think that as we move forward in medicine, what we're seeing are that the sensors and the effectors are on the same platform, and that so that you can use a device such as ultrasound to not only sense where a stone is, but that you can actually use higher energies, for example, to manipulate the stone or to even destroy the stone. And what happens in this mid-range between the sensing energies and the lithotripsy energies is that you actually excite air bubbles and gas that's trapped in the stone. It actually twinkles and allows you to identify where the stone is, and then the stone gets excited a little bit and you can move it. And the new generation of urologists grew up as gamers, as video gamers, and they're actually excellent at having three-dimensional sense of the kidney, and it's absolutely fascinating to watch them excite these stones, and they can actually dislodge them from the calyces and move them down the ureter. And boy, it's a lot better than having a cystoscopic procedure or something like this.
Okay.
Thank you, Professor Sutton. You gave a wonderful lecture. I appreciate very much that you mentioned in your report that the joint research program for the U.S. and Russia for young scientists. That could you please to give more comments on the international corporations on for the young scientists? You will make more comments on this.
Yes. Well, because of time, I only picked one or two examples, but I think that it's a reality that the postdoctoral workforce is to some extent the scientific engine, the scientific workforce internationally, and it's already in place. There are postdocs who train in their own country and then go abroad. There are postdocs who go abroad, some stay abroad, some come back. And so I think that this is a natural infrastructure for international cooperation and collaboration. If you want two laboratories from different countries to work together on a project, you have a very motivated workforce in the postdoctoral students. But of course, there are many other areas and levels of education, whether it be at graduate and undergraduate, and of course you want to capture the imagination and the inspiration of young children. There are opportunities within the medical schools, and there's continuing opportunities as well, which I think are very important. And I would include among those this forum.
Okay, thank you. Because time is so limited, thank you very much, Dr. Sutton.
And make my presentation. First of all, I would like to stress that we have an experience of development and support space missions from the beginning of space age, and this experience work with a lot of space centers, space stations. We have about 5 space stations, and now successfully working the international cooperation on the board of the International Space Station. Of course, this gives us knowledge, technology and experience of their usage. If we look at the physiology and space medicine summary of the results which have held during this period of time, we can see that we have some new knowledge in the field of risk factor of the space flights, how the space flight and weightlessness conditions influence on human organism, and how human organism answer on these extreme conditions. So we know now more about our organism reactions on external conditions, and all these give us possibility to use our knowledge for public health system. You see how many changes are happened during the space flight in human body. Let me not read all of this, you can see it on the slide, but you see it's a lot of reactions from nervous, cardio, endocrine, immunology, bone system, and so on. All these reactions, some of them are physiology, some of them are not physiology. The organism try to adaptate to new conditions, and it's very interesting to see this adaptation process, this adaptation syndrome, and try to find the line between adaptation and disturbances which then can be happened. This knowledge gives us possibility to develop countermeasures and training procedures as devices which we use in this process, and after then we can see how these devices and this methodology can be used for public health system. New knowledge. Let me summarize a bit what I'm talking about. New knowledge, first of all, it's a healthy human norm and body reserve capacity. Then syndrome of hypokinesia and hypodynamia and its effect of human body. And then we compare some conditions which happened during the space flight, some physiological changes, clinical changes. We compare it with what we'll see in healthcare practice, and we understand that somewhere we compare, and our knowledge can be used for clinical practice. And of course, methods and technology, what I'm talking here about, can be used. What does it mean, level of health, norm, and pre-disease condition? It's very important conclusion from this practice. It means that clinically healthy guy can have different level of his physical and mental ability, and can react in different way for this and that situation. And it is understandable that we should know the level of his physiological health, because it's some sort of disease diagnostics. knowing that, we understand how successful he will react on this and that extreme condition, and know how we can strengthen him to be more ready for such work. The next level, pre-disease and pre-morbid states, it's very important because this gives us possibility to try to diagnose condition changes in a human before he feels himself ill. That's why we can work with so-called healthy people and test their conditions and give them experience, give them advice how they can strengthen their health. It gives us the knowledge of so-called health of clinic of healthy people, and we try to introduce this ideology to the public health and health care service in Russia. And of course pathological state breakdown in the adaptation, which is more or less understandable and very useful for knowledge of this is very useful, of course, for the clinical diseases. As an example of some technology, some methodology, some devices which are now introduced to the public health system, it's express diagnostics for cardiovascular system, because we use it the method of diagnosis not only changes and pre-morbid states and functional reserves of even cardiovascular system, but on the base of cardiovascular investigations, our knowledge gives us possibility to understand and make the conclusions about the level of health this or that person, and make recommendations how we can strengthen. Some another examples which are used in this case, and one more example, reserve device, which is an attempt to combine the different investigation in one case, which can be useful for mobile crews and for screening the health care of groups of people all over the country. Hyperkinesia. Hyperkinesia, it's the K disease, maybe K disease of our century. That's what we see in weightlessness conditions, what we see in our model experiments. By the way, it's one of the model of space flight conditions. Bed rest, what is it? It's hyperkinesia, hyperdynamia, dry emission is the same. But you see that we face this situation in clinical practice when the people should lie in the bed for a long period of time. That's why they are in the face of hyperkinesia, and physicians should cure not only the direct disease but this syndrome too, and pay in the attention. And you see that some of us are faced with this syndrome in our everyday life. It's now the syndrome of so-called middle economic class. This is a syndrome of successfully developed societies. So it's open as, it's a problem, great problem of course, but at the same time it's open as a huge market of introduction of our knowledge to help people in their everyday life. As an example of healthcare screening methods, I would like to show you health navigator technology. This technology based on this very simple screening test of physical and mental ability of the human body. They have a huge number of database, measured about 700,000 people of different age, and this gives them possibility on the basis of the simple test made the conclusion about the condition of the human body and make recommendations how to solve the problem, and then test the result of this work. Of course, if we should work with the middle economic class, try to fight against hyperkinesia, we don't should forget about psychological problems of our modern age, and so space medicine can give some new approach, new technologies to that. Then I would like to talk here a bit about possibility to introduce health care technology directly to the clinics. For example, this is a so-called dry immersion model for weightlessness condition with using on a regular basis in our institute and in other institutions. But our findings show that it can be used, and it's already used, and we have some results of it for treatment of some cardiovascular disturbances, high pressure situation, and some other situations. You can read it on this slide, and we are working with introduction this to the clinics. Some other technology based on the correction of sensomotor foot afferentation maintenance can be used in rehabilitation process. At the same time, of course, they should be useful in the special neurological clinic and the clinic of brain disorders. Some of them are more or less popular, not only in our country but abroad. It's Reagan and Corvette suits, and our scientists or the clinicians receive a very prestigious national award for these devices, for this technique. It's very successful in rehabilitation and neurological clinic.
Back at IMBP, we're making sure our muscles don't wither away in space, leaving astronauts and cosmonauts on a long road to post-flight recovery. On Earth, gravity's effects build us up by holding us down, maintaining basic body strength by giving us weight. That's all afloat in space. So IMBP and other researchers have to manufacture methods of combating the muscular atrophy and bone deterioration facing our space travelers.
If one of the problems with staying in space for a long time is not feeling yourself weighed down enough to get any muscle exercise, this is a pretty exaggerated solution.
But that's literally what it takes. Lacking gravity as a source of body-loading tension, exercise in space has to create artificial sources of resistance. Otherwise, ISS crew could pump massive iron without ever getting buff like Arnold. Specially made suits also provide an important passive method of mobility resistance, since space missions are high-precision operations, with serious demands on the crew's time. This Penguin 3 suit developed at IMBP helps turn every minute into a bit of bodybuilding. Today's Penguin 3 is an evolved version of that earlier spacesuit, now with sensors offering the ability to control precisely the amount of force applied by the elastic cables as resistance against various muscle groups. The basic design has been preserved, allowing for passive stimulate the nerve endings in the feet that control our walking muscles, slowly reminding the brain what it takes. A new lease on life from extraterrestrial origins.
What another field of implementation is the conditions of extreme medicine, because working with astronauts on the landing process, we know how we can serve very quickly people in unusual conditions in open air, and our results of our investigations already are implemented in the practice of emergency systems, and of course telemedicine. It's well known. It's a good example, good practice of implementation space medicine technology to the public health system. We work with underwater medicine, and so develop a large number of devices which give possibility to patients to use warm mixtures, gas mixtures, and inert mixtures, inactive so-called gas mixtures, for treatment of some disturbances in lungs. And by the way, this technique can be used in some physiological practice, like in sport. Sport medicine is one of our direction of our movement, and this gives us possibility, our knowledge coming from space and our little space sport practice give us possibility to develop devices for rehabilitation of patients. Some of them are, as an example, shown on these pictures. In our practice, we work on the base. We have an innovation council of our institute, and works directly with our customers and with our partners in the clinics, but at the same time we try to organize common units in some of clinics. They are already done for investigators of new methods, and try to organize innovative circle around the institute, small innovative companies, which we send our technologies, give them license for implementation of this technology, and they try to do this business. Of course, we do everything with the conditions of intellectual property safe, and try to introduce our results on the market, participating maybe yearly in 5-6 exhibitions every year, and have some good results from these exhibitions. We will continue this work. I could say you that our state put great attention to new technologies implementation to the public health system. I can say this as a member of the Council for Innovation of the Russian Academy of Science. But I think that we should change a bit our approach now, because from the beginning we find some new knowledge, we develop new technology, and we develop a new technique, new devices, and then try to think how it can be used for public health system. Now I think that we should change this ideology. Now, planning our new investigators for a space program, we should think how the result can be used for public health systems. This means that even we not flight to the Mars for decade, for example, but the result of this work should be introduced to the public health systems during this way. I think it will be very important part of ideology, strategy of the work of our society. And at the end of my short speech, I would like say that of course we actively work, and we hope to work widely in international cooperation. Thanks, Jeff, make a brilliant examples of cooperation with NSBRI. And I would like to thank, first of all, our astronauts. Many of them are there. Thank you very much, because you are people who open new stages, new wave, our mankind to the universe, and give us new knowledge and new methods which can be used in publics for everyday news. And I would like to say thanks to our volunteers in the phase of crew member of Mars 500 experiment, because these guys put on the table of our science not only their time, their knowledge, but sometimes their health, and open new possibilities for thousands people on the earth. Thank you very much.
Not of myself, but the answers of the community, what the people want to do in the future. I list only 10 and not the 5 which are lowest priority. And the 10 I list here are very interesting. They can be divided into 2 parts. It is clear, and it was also clear during our discussions at the symposium, that the whole life sciences community is supporting human exploration and supporting the need to do all the operational tasks for exploration. At the same time, I was very surprised that most of the scientists said we want to do also basic research. We want to use the opportunity in microgravity to find out about human physiology and to find out about things for clinical medicine. And so there's a strong wish of the community to link between the space and the terrestrial medicine applications. And so this means Earth-space collaboration and also global collaboration is what the community wants. So the future challenges for space medicine, I would say, are for sure enable human exploration and also use the tasks for life sciences for general knowledge. I give here one example of a recent development that's coming from space and that has a lot of implications on terrestrial medicine. Here you see on the left side a very simple ground out, and it's in the textbook the medical people all know. when you have water and salt and a healthy person, in 2 weeks, the same amount which goes in will come out. And there's always parallel water and salt. That's textbook knowledge. This astronaut behaved differently. He followed the textbook on Earth, but in space he excreted the water, but he did not excrete the salt. He stored salt, not allowed. So much acidosis should be involved in bone metabolism, because acidosis means osteoclast activation, and indeed when you have high salt ingestion, you start to lose bone very quickly. Bone degradation is increased. So a clinical finding which is important for our society: salt ingestion is not only bad for your blood pressure regulation, but also for your bones and also for your muscles. Now our colleague Dr. Titze, he looked at those rat tissues and found in the skin that there are macrophages going into skin, and macrophages going into the skin, and there is an overexpression of blood vessels and also lymphatic vessels. So there was a strange finding, and then when the macrophages are inhibited, then suddenly those animals, test animals, developed high blood pressure. So this is now a very important finding, because suddenly now blood pressure regulation is not only done as it is described in our textbooks, but suddenly blood pressure regulation has a link to the immune system, and the immune system is involved in it. This is certainly important for astronauts, but I think it's extremely important for understanding blood pressure regulation. If we understand these mechanisms, we have new tools also for treatment of high blood pressure. Now, as there is salt in skin, then the question is it possible to visualize this salt? And then Dr. Titze went to the respective company in Germany at the same town in Erlangen, which develops magnetic resonance imaging. And then there was a new technique, sodium coil development on magnetic resonance. And here you see on the lower left side, young healthy people. You can see how much sodium is stored in their body, have little sodium in their body. You see the skin is white here, so a lot of sodium is in the skin. The other tissues are not so white. But when you compare this with an aged person which has high blood pressure, then there is a huge amount of salt. And the water storage is completely the same. There is no change. So this is an indication you can even visualize the salt. So we think that probably in the future one does not only measure the body mass index, but also you can visualize the body salt index. And it may be that this is an indication of aging and has a lot of other implications. So a very, very simple, tiny finding suddenly is starting to change how we look at a lot of diseases in humans. Now, this tiny finding was published in 2000, is now cited about 60 times or so. But the next paper of a group of Titze in Nature Medicine, I think, is already cited over 100 times. There's another paper in Nature this year, and because the finding that the immune system is involved in blood pressure regulation on one side, but is in Earth applications. Currently, the people who work on this field don't know anymore it comes from space. They have no connection to space, but it would not have been found if those observations would not have been made. This is just one example of why it is important to really link up with the terrestrial medicine and to have this strategic link. Now, coming to strategy, economy is always important also for for spaceflight, for funding of scientists, and therefore there's always the question: does what we are doing, does this have to do with economy? You probably know the so-called Kondratiev cycle of economic development. that cotton was a boom, and railways were a boom, and so on. Last boom was information technology. Currently, information technology is booming out. The Apple shares are falling right now. It's still the next booming industry is coming, and there's everybody thinks probably life sciences will be the next one. So that we have to ask ourselves, is what we are doing when we link up with terrestrial medicine, what might it have to do with the coming cycle? And therefore I now simply took the global challenges for the future and say, well, what we do, does it have to do with the global challenges? Is there a connection? Could we play a role here? And you see health, for sure, health is a mega trend, and also the democratic development is a mega trend. And in this mega trend, one has to focus in the future on staying healthy, on the prevention. Now we are specialized in keeping healthy, high performers healthy and able to perform high, and they are kind of a model for this application. So now is able to work and to be happy when they do their 2 or 3 hour fitness training every day, but also to see them as models for the tasks of the future. And I also think we should not forget the future spaceflight participants, even if they are not, even if they just fly up to 100 kilometers and down, because they are probably very open to support pilots, managers, and the general population in a stepwise approach. Everybody accepts astronauts are the best treated people, and what is done in astronauts should be also done in others. Keeps them slim and so on. Now, in medicine, we are currently in the phase of the omics. The omics is what is down here, but at the end, omics, we need individual predictions of the risks. Jeff talked a lot about it. Individual risk for the future, and where do we have to do the optimal prevention. So the future main challenge is to put together the whole thing and make individual prediction on individual humans. As we have so much information, I think an extremely important thing is the modeling for individual predictions. And in modeling, you need, as a starting, you need basically 2 groups of people. One is the epidemiologic approach, but other is to look to individuals and to look to individuals under defined conditions. And in our field, we are the only scientific medical community which is studying healthy subjects for a long time under highly defined conditions like the Mars 500 crew. Nobody else in medicine does this, and so this is also an important asset for the future of medicine and of space medicine. Now, for ourselves, we said, okay, if we want to do those tasks, if we want to optimally prepare for future missions beyond Earth and beyond Earth's orbit on the one side, and if we want to optimally link with terrestrial medicine, then we should have the optimal facilities for this, and therefore we have had the opportunity to build a facility which was shown already today, a facility where we can isolate people, where we can have up to 12 people and do physiology on them. We even have an MRI. It's an MRI with the first commercially available sodium detection methodology, and we certainly have a human centrifuge for the future of the space flight applications, but also for clinical applications. And this is something very good for the future research. But also it contains a lot of space for public outreach, for showing what we are doing, for linking up with people. And therefore in this whole facility it's also possible to have events, to have conferences, even conferences of business people or some other people, just to expose them to what we are doing. I think this is an extremely important task here. That is how it looks. For the future, we should, I think, not only work with our own fields. Globally, there is the global collaboration in space physiology. I think we have also the model of, we have so many collaborations already. We should really strengthen and intensify these collaborations in a swarm approach. It is dangerous, like here, if the key fish always makes circles, then everybody makes circles, so swarm intelligence is also dangerous. But I think we should use our joint thing for joint strategies in the future, as we do already. But I think the link between terrestrial funding and space funding should be intensified. And that's basically what we are trying in our institution also, to have a mixed funding in the future, certainly from space, but at the same time from terrestrial funds, from our possibilities, but also to find new approaches in new ways, which means also people who give individuals who may fund things, even crowdfunding possibilities. So new ways of funding should be found. That's what we are going to do in the future, and that's what I hope will the community also do in the future. And with this, I thank you very much for your attention.
Yes, thank you, Dr. Geza. Any comment in the question, please?
Igor.
Please.
My question is that, the question is that I'm very interested
to do an MRI with a sodium 23 coil. So you should buy the machine from this German company. And then you can just visualize. But there is also a measure, there is a proteoglycan are involved. So if you have a lot of sodium storage, then the proteoglycan side chain expression is increased. So you can also do a skin biopsy, not looking for sodium, but for the proteoglycan expression. This is possible. This works very well. So when Jens worked it in rats, we did it in humans. It's working. So either skin biopsy or MRI.
Approach, or maybe the approach of the scientists you ask, concerning the two alternatives, or maybe a synthetic way. First one is in the prospects, which is preferable to use static state and markers of some possible pathology, or to use, for instance, intermediate reactions from healthy to disease in order to understand the situation and in order to make good prognosis.
I don't know whether I completely understood your question. So is the question how much sodium should a human be to be have to be healthy? Or?
No, I mean the global approach concerning the, for instance, loading tests have some evaluations of the reactions in intermediate stage. I mean on the process between health
forum, and he is the director of the state key lab for the space medicine fundamentals and application. Yeah, from the China Astronaut Center. Yeah, Professor Li, please.
Okay. So I'm not to introduce more. As beginning, I would like to see. We would like to thanks for the Global Network Forum have an opportunity to have this one, and also thanks for Dr. Chen to design this forum and this topic. People know health problem is due to the biggest challenge to the mankind, and also we would like to think about what is the future of the medicine and so what is our life in the future. For the people, we have 45 years flight, so people got lots of understanding of the effects of the microbiology. And also, we have lots of new knowledge from the space flight. But for the future, the safety and the health, especially in the challenge for the people. At this moment, before I introduce our mass 500 people, they are seated here, please. Dr. Wang, could you introduce your colleague one by one? Please.
Thank you very much. Thank Professor Lee, thank Professor Chen gave us it's just like an amazing opportunity to bring our Mass 500 crew here. And here is my friend, my crew member, Roman Shah.
Hello everybody, thank you for this opportunity. I will just pass the microphone for the other to give their names.
Thank you for preparing this congress. This is very interesting and I think very...
Представили, я был командиром экипажа, Алексей Сетев.
Alexei Sitov was a commander of Mass 500.
Okay, thank you.
Я потерялся.
Thank you.
Yeah, thank you very much for all of the 500 mass crew member. Okay, it's wonderful. Yeah, please continue.
So here I will in this experiment lots of data will be get. Just for example to introduce a little. Here we have some data from psychological and from biochemistry parameter, and also we have some molecular exchange tests. And here we see with this slide it shows you the model state. We have 6 kind of model state. One is tensional, and another one anger, fatigue, and disprice, and vigor, and confusion. This is interesting. Is with this analysis from the before the cupping and during the cupping and after the cupping, we had found some model state is more related with methylation. Here we see this one. Here in the about 150 days is more obviously different for the methylation. So I think this is just an example for this kind of experiment. We can got a lot of data. This data is we wouldn't get in the normal time. So as the time is going to the traditional medicine and evidence-based medicine, and also with bioinformatics, we got lots of big data and new data. Also, we have some new discovery and new knowledge. So one hand is we got lots of data and is relatable with health, and another one is we are Chinese. We have a traditional medicine. For the traditional medicine, we have we just think about we have some little different for the concept of the disease. For example, the people that say the Chinese medicine say the same disease with a different reason, and also same different malady, but the different phenotype. So this afternoon we have I think is professor and doctor of traditional Chinese medicine, they will discuss more details. But here, I think the concept of the holistic approach and the special treatment technology or technical is a bit different. So we just think about how to confuse this Swiss medicine and traditional medicine and the people's health. As you know, in the 10 years from 2003 to 2013, we have in the 10 years we have 10 astronautics and 12 passengers go to the space flight. The maximum the flight time is 15 days. During these 15 days, we must face the health risk. So one hand is the clinic disease risk, and another one is what is physiology risk. During this flight and this project, we established our space medicine system, including four parts. One is space medical monitor and support, and another one is what lateness effect and countermeasure, and another one is psychological supported, and also including the nutrition supported. For the space medical monitoring and support, we have three parts of work. One is during the space flight, we have monitored the health situation, like the cardiopulmonary function test, chemistry test, and spacecraft microbial detection and control. The second part is about clinical disease prevention, and also it is including lots of standard. This standard is for to flight substances, and it could be flight. And also important is about the medical treatment solution preparation in advance. So this three part is the main part of the space medical monitor and supported. And also the second part is very important is what is physiology effect. Lots of people, all space medicine people know what's happened during the flight, during the long time flight, muscle atrophy and cardiovascular dysfunction and bone loss and etc. So with this part, we have 50 days, 30 days, 50 days, and 6 days bed rest experiments. With this bed rest experiments, we test or measured in the flight. Here, based on our bed rest results, some countermeasures was successfully to use in the Shenzhou 9 and the Shenzhou 10. The flight, the people, the astronauts, is effect. And also the psychologically supported, including psychological selection and psychological compatibility training and stress management and relaxing training. Also, we have nutrition supported. One part is for the research of the study, the space nutrition and metabolism, the requirement and the standard. Another one is the Chinese food. Lots of people know is more complicated, so we must to develop the technology to production or Chinese food in the space. Also, as a meantime, we developed some space medical experiment device. Here, after now, we could do some physiology experiment with cardio function, with brain function, and also for the we developed an automobile cellular culture device. With this device, we could fix culture the cells and fix cells, and also we could with different drug on the cells on the flight. Then we could get the image and the DNA and RNA samples. With Shenzhou 10, we have the experiment is about integrating RVRV and beta-3 precipitate in the response of CBF1 is a promoter of the osteoblast. This promoter could response decreased in the microgravity to IGF-1 under IGF-1 Also, we developed a special device. It could set up space bimextral detection. This device is based on the surface plasma response SPR technology. We could monitor the 3 nutrient terraces. This bimextral molecule could relax the stress level on orbit. Also, we have lots of basic research, some questions, hypothesis, organism interaction, mechanism of bone loss in space, and the mechanism of cytoskeleton regulating signal perception, and some new mechanism of transmission and response. Also, we have some macro 124 is a target as ATF4 to the inhibit bone information. Is published in the Nature Medicine, the PI was Dr. Yin Xian. And also we developed from human and from human to animal to cellars device to could do some seriously experiment about the simulated microgravity and all rate effects. Also, we established a platform. This platform is we collecting the lots of data is from the people's space flight and also the spatial training and the spatial long time experiment also like a mass 500 and also the best rest experiment. Another part is the data is come from the animal research. Is maybe molecular and cellular mechanism. So with this data from the physiology effect and the molecular and genes expression, we could know what is happened exactly in the mechanism. And also the traditional medicine is very special in China. So I think this could be contributed for the space medicine. As you know, the 2012 the China will establish the China Space Station. This expedition for this expedition, we must to face to the challenge is about long-term stay more than 118 days. So the one challenge is for us is to develop the countermeasure for the microgravity, and another challenge is this is open platform. We could do lots of experiments how to have the innovation, the experiment. So in the space in this space medicine and the people's health, public health, we also think about we have lots of common problems faced by the space flight and the popular medicine. For example, the bone loss in the space, we know we have bone loss is every month we have 1.5 degrees, and also we have increased the risk of fracture after reloading, and also renal calculus and dorsal cerebral. And on the ground, we also have lots of people more and more. The older people has osteoporosis, and also we have rolling calculus and hypercalculism. Also some lots of metabolism syndrome, like diabetes, ulcerative, and hyperlipidism is a little common problem. So the function, the next step is with the space station and also in the ground model, we could do some research is about the relative between the bone and the immune function change under the microgravity condition. And another link is between the both and the subclinic debates change during the space flight, and how about the decrease the male genital function and space bone loss, because now we have recent years we have several papers to describe the relation of the male genital function and the metabolism of the bone loss. And also the screen the new biomarker of the space bone loss from the circulation microRNA. And also for the cellular mechanism on the space bone loss, such as co-regulation with BMS and osteoclast and also to have a cooperation with the other teams and other ACs. So, I talk about some common questions from the space flight and the public medicine. So I think for the future, we could benefit from the many space medical biology knowledge and experience. And we also like to benefit from the popular medicine and the largest knowledge of the life science. Also, we think we could benefit from the unique Chinese healthcare scale and habits. I got some ideas from the Dr. Zhao. For this purpose, we developed the NUWA project. NUWA is, I think, last year I introduced some story about NUWA. It's a Chinese traditional, is a historic Chinese story. These ladies could create living things and take care of people from the diseases. So we made this ideas for this for the name of this project. This project we focus on the bone loss, muscle atrophy, and cardiovascular. Even for the space flight, and another part is for the public health care. We would like to, with this obviously and the identifications and our people do not do what we are focused on, we could cooperation as it is more effectively. So with this project, we will send the more details about the work about the schedule and the planning of the project. So that is my talk. I think we would like to think about what are the contribution from the space medicine and how to fusion of the astronauts and public people, how to fusion of the theory and application and fusion of the space and Earth. In China, we have the old story is through our break in order to get a game. That is, they offer a few comments, remarks by way of introduction to, so that we can put together other people's come up with valuable opinions. So this afternoon we have two panels, panel A and panel B. We can discuss more details. Thanks.
Thank you, Dr. Lee.